Hello folks, and welcome to a new fairly short series of videos that we're going to be doing relating to projects that I have undertaken using the open source inverter system designed by Johannes Hubner. So there have been several iterations of this that I've been involved in. But just to go back and give a very brief history, when I got the Panzer, I also got, courtesy of EVTV and New Electric, a Siemens 1PV 5135 AC motor, complete with the DMOC 645 controller. Now at the time, EVTV had designed a system to allow that inverter to run as it had been intended to do in the original Azure Dynamics application. However, I tend to take the long way around and the hard way around in these particular things. Thus I decided I wasn't going to do that, but rather I was going to rip the guts out of the DMOC, use the power stage in conjunction with that system, purchased in a kit form from Johannes Hubner. And I did that, and it's been running away very well now for the past few years. And it's been through many versions of drivetrain, as you will see if you want to go back and poke around in some of my video vault archives. Why would you want to do that? But anyway, so recently, as you will probably see again from the videos, I've been very much involved with the Tesla reverse engineering projects, open sourcing, all that, and I've been basing the logic boards that I've designed for the drive units very firmly around the open source inverter system. So before getting into the Tesla stuff, I had designed a few different versions of the PCBs just to make them a little bit more friendly for myself. And they're about a year, maybe a year and a half ago, I had purchased a very cheap AC system, complete with motor, gearbox and inverter from a gentleman in the UK. And it was called the Enova drivetrain. Now I know that several people have purchased those units, and I went ahead and designed a PCB that would allow you to, again, kind of similarly do what I had done to the DMOC 645 with the Enova inverter. So you would take out all of the Enova control systems and plop in a PCB. And in fact, let me just grab one. So I designed this particular PCB, and it went through several variants. Version 8 is this one, which is the last one, and I had a few of these professionally manufactured and sold about 4 or 5 of them to people wanting to use the Enova inverter. Just due to some changes in circumstances recently, I'm not really going to be in a position to do that anymore. But what I did want to do was to make an instructional video to show you guys how to use these. And I started thinking about it some more, and because there's quite a lot more to it than just the Enova, I'm going to break it down into a series of videos that will hopefully, number one, show you how to use these PCBs. Number two, will run through the generalities of how the system works and how to run a motor with it. So things like how to set up the PC interface and all that kind of thing. Um, so all of the files for all of these modifications to the inverter system that I've made are available on my GitHub, and there'll be a link in the description to that particular repository, I believe they're called. I'm not a big GitHub guy. I just throw the files up there and people do strange things like forking and committing and uncommitting and pulling and pushing, and yeah, okay. Anyway, so this is where we're going to start off. So what I'm going to do next is I'm going to jump on the PC and I'm going to pretty much show you guys where all this stuff started off. So stay with us. Alrighty folks, so here we are just on the PC at the minute. Unfortunately running Windows because this is where I basically do my PCB design. So I'm going to take you to the website of the inverter, and as you can see there from my history, it's one that I still visit quite a lot today. So this is the front page, and I'm not going to run through the whole thing, but I just wanted you guys to see basically where the whole thing started off from. And Johannes originally designed this, I believe, to run his own car, and it's since kind of taken on a bit of a life of its own. Quite a lot of people have gone ahead and built this and built versions of it, and it's continuously under development as well. And there's some really neat things being added to it, not least of which is the Tesla stuff that I'm working on, but there's additional things like battery charging. So for example, the inverter will use the motor as a buck or a boost in inductor and allow you to do pretty high power charging from either an AC or a DC source. Everything is very well laid out here on the website. There are videos showing how to set the thing up, and various circuit diagrams and explanations about how to set stuff up. Now, I myself, when I first began working on this, it took me a while to get my head around some of the way that things worked, but once I've kind of gone through it a few times, it's kind of became second nature now. So at least some of it, there's still a few surprises in there. So I'm hoping that I will be able to show you guys how all of this stuff comes together and how it works for me, and particularly in today's video, how it's going to work out for the Enova system. So just as a last kind of a point here about the site here, the thing to keep in mind is it is 100% open source, so you can basically from this page here you can pretty much download everything, source code, binaries, PCB layouts, bombs, the whole lot. So this is where it all started, and this is where it still goes on, really. So alright, let's go have a look at one of these Enova inverters and see if we can make a bit more sense out of what we're going to be doing. Alrighty guys, so we're back out in the workshop, and you will see here is a stack of 4 Enova inverters. Now you may be thinking, geez Damien, you know, what are you going to do with 4 of them? Well, what's going to happen to these 4 is going to be part of this video series as well, so fear not, we will be sharing. But in today's episode, what we are pretty much going to do is going to show you how to modify one of these guys to work with our open source Combi PCB. So, before we jump in to getting the cover off, I'm going to basically show you what it's going to ultimately look like in the shape of my drift turkey crazy car. So, if you've been following this series, and of course you have, because you follow all of my crazy videos, you will know that this is a BMW E46 that I purchased about a year and a half ago on a complete whim because I was going through a difficult time. And of course, what do you do when you go through a difficult time? Well, you buy a car. So we have here the Enova motor. Hopefully you'll be able to see this now. Installed in a kind of a mid-engine type setup here. And you can see in there hopefully the gearbox and the short prop shaft that drives this particular mess. But it has worked out as a very good system to allow me to prove and to debug the control board that we're going to be, well, that basically you guys are going to be using for running these motors. Now, of course, just to be very clear, this is not the only way that you can run these. There probably are ways to hack the original drivers, firmware, all that kind of thing, but I pretty much just jumped straight ahead and went for this guy. So let's leave this now and we'll go back inside and we get the cover off, and I'll be able to show you the steps that we need to take to install this particular PCB. Alrighty, so once we get out all of these screws, they can be a bit of a pig because, as you'll see on this one, the heads tend to be rusted and full of kind of dirt, so you really need to get that dirt out and make sure you have a very good fitting screwdriver, otherwise you're going to wring them off. So once we've all the screws out all the way around, we're going to go ahead and pop the lid off this guy. Alrighty, so my phone just keeps beeping today. I'm so popular. So once we get the lid off, we're going to reveal the guts. And there's quite a lot going on in this particular box, because it wasn't just a motor drive inverter. Additionally to that, in here you had a smaller inverter, I believe, to drive a power steering pump, and a DC to DC converter running around this PCB here. Now, I haven't actually really investigated any of these parts, so pretty much what we're going to do is we're going to strip out all of this stuff here, and we're going to concentrate on the power stage, because in this whole setup here, the only things that we're going to reuse will be the power transistors, the DC bus, and the capacitors. So from here over, we're pretty much going to just strip it out. So let's go ahead and do that. So that's just removing these tie down bars. Again, all of these tend to be very tight. the next phase of the operation is to always ensure you use a sandwich bag for your screws, as we do want to be able to reassemble certain parts of this particular setup. So they need to go and be put away safely. And okay, we'll leave those, we'll just tape those to that box there. So once we get this stuff cleared out, there'll be a few things around here that are important that we need to point out. So I'm going to go ahead now and remove some of these wiring bundles. Now, some people are probably thinking, well, couldn't we reuse the driver board and, you know, maybe even, you know, make a board to run this driver board and all that? Yeah, we certainly could. At the time that I was doing this, I just basically didn't deem it to be worthwhile. That's not to say that at some point that it's, you know, we may look at doing something like that. Now, bit of a sore back, so I'm going to go ahead and grab a chair here. Now, in here on the front of the driver board, you're going to see these 3 white wires here, and these white wires are leading from the 2 phase current sensors and 1 DC bus current sensor. So we're going to want to disconnect them, and unfortunately they kind of use this goo. It's not as scary as the Tesla goo, and they do come out, you know, quite readily. So we just unplug these lines here, you know, being careful as we can not to damage them. But having said that, we are in the application with the combi board, we won't be reusing the original current sensors. We'll be fitting a newer type, but for the application that I'm going to be doing with these inverters, I may decide to reuse the existing sensors. If that is the case, of course, that will be all made available and you can modify away to your heart's content. Now, there are several low current, high voltage lines that come from the DC bus bars over to other parts. For example, this one here would bring current from the DC bus to the low power steering inverter. So we're going to go ahead and just unplug these rather annoying spade terminals that have a kind of a latch on them, but they come out, you know, fairly readily as well. There's another set here that would be used for the DC to DC converter. I'm going to go ahead and unplug those. I realize this video will probably be only useful to people that are, you know, working on these inverters, but by the same token, you know, it's kind of something that, you know, it's fairly popular now. There's quite a few of them out there, and you know, I want to basically be able to try to help people to get them to run. Now, so once we have those cleared away, the next one here is a kind of a multi-pin that goes to the original logic PCB. So this one will take a little bit of wrestling because of the goo again. You know, I can kind of try to just clear away some of that. By the way, I hope you guys enjoyed the live stream. Maybe I should be live streaming this. This should be super boring. Here we go. Now, well, I think I'll be doing a live stream on a kind of a semi-regular basis now. Might as well try to lose all the subscribers that I have. Alright. Should be able to get this one loose now. Well, it's fighting. We need a screwdriver. Alright, so we're just gonna, there it is. Okay, so we're kind of gradually now starting to free up some of the connections. So then the next thing we want to disconnect are our 3 IGBT driver tails. Now these we will be reusing with the with the open source logic board. And again, they are completely covered in this goo. So you just gotta try and, you know, do your best to. Really, we won't want to. I don't want to damage anything here because, you know, I particularly don't want to damage these plugs. So, hello. Let's see how we get on here. I'm just holding down the tab and just kind of pulling them out against the goo, which, you know, seems to be working okay. There we go. Come on, last one. There it is. Those are our 3 tails out. Now these tails will plug directly into our combi board. There's one more that we need to disconnect in here, which is the DC bus sensing and the discharge resistor. Again, it's just a case of just fighting the goo. And just trying not to damage anything. This doesn't plug directly into the combi board, so, you know, it's probably no really big deal if you do damage it a little bit. Now, there we are. Okay, so we've now completely separated the power stage from all of this old driver crap. So next thing we want to do now is remove, oh sorry, there is a couple more, I'm lying to you again. There's a couple of more here, and one of them is particularly important because it contains the encoder and the motor temperature sensor, which we will need to reconnect to our logic board. So let's go ahead and just cut away here with these cable ties. These white wires, by the way, are just a high voltage interlock thing, similar again to what Tesla do, but, you know, kind of a basic version. So I'm just going to unplug this. I might even just cut this because it's not going to be something I'm going to reuse. Just make life easy. And again, this plug here, which has the encoder on it, we want to be careful of. Just get it unplugged, past the goo, and there we are. It's this cable here, this grey cable that has the encoder and motor temperature sensor in there, and we will be needing that. So one final thing, there's a big huge ribbon cable here. It is in an ejector socket though, so it's not that difficult to just pop the tabs on it and work it out. Again, that's not something that we're, in the current design, that we're going to reuse. So right now we've got this sandwich of the old logic driver boards is pretty much ready to be removed. So I'm going to grab a long screwdriver now. Now we got some screws to remove. So let's see. I don't know if this one will reach with it. Just about, yeah. There it is. There's one loosened. One more, of course, here hiding in a difficult to get to location, but I think we've managed to get it. We've broken it loose anyway. Yeah, we did. That should be all those screws out. There's only 4 of them. Like so, and it's out. And that is our old logic board and driver board removed. Alrighty, so now that we have the old driver and logic board out, The next thing that we would do here is to basically strip out all of this old DC-DC converter and smaller inverter and these various bits and pieces that we don't need. Now, in the interest of not completely boring everyone to tears today, I won't do that. Rather, I will just run through the next few steps that we would need to take to install the logic board. Now, physically installing the board, and again I apologize that I don't have a fully populated board here, I've just got the bare one, but I'll be able to show you on the drift car board. But what I simply did was, we have a series of drill holes in the back of the PCB, and I used some self-adhesive PCB pillars. I'll see if I can find a part number for you guys that we can supply. And you just basically pop the pillars in, peel off the backing, and you come along. We would be basically leaving this metal part in here. You just come along and you basically just position the board as close down to this end as you can, because some people may want to put the lid back on. And you basically then stick it up against the aluminium here, and it gives you your PCB mounted securely to this piece of framework here. So that does need to remain in the inverter for basically mounting the PCB. So before we do that, there's a couple of little support bits that we need to do. Now, I mentioned one of those is the encoder. And the encoder comes in through a kind of one of these twist lock type plugs and comes up into the inverter properly through this multi-way kind of plug here. So it joins forces with a few other things that we don't really need. So I'm going to just go ahead and show you guys the bits that we do need. Now, there's a bit of this heat shrink here, so I'm going to get rid of that. Let's see if I can get a knife. That's not a knife, that's a knife. We'll get rid of that bit of heat shrink, because I want to be able to show you guys kind of the various bits that we need to do here without slicing my own hand open, preferably. Yeah, all the fun of the fair, because it's blunt, of course. Nothing more dangerous than a blunt knife. Yeah. Try this one, it might have a bit of sharpness to it. There we go. Alright. Progress. Damn, this really hates me. Nearly had it. Okay, so once you get rid of that and get rid of the blunt knife, you'll see that this plug breaks down into two parts. We have these loose wires here. We have the wires coming in on this kind of screened cable. And so let me see here now. I'm going to just take my wire cutters. I'm going to cut off the bit that we don't need. I'm going to retain our screened cable here. Now, you will see in this there are 6 colors. There's a motor temperature sensor. There is a 5 volts, a ground, and our 2 encoder channels. We'll be using the motor temperature sensor, 5 volt ground, and 1 of the encoder channels. And I will get the color code of this for you guys and let you know what colors that you need to do. There is a little bit of loom wiring that we need to do in order to fit this particular board. So, next thing that we would be doing here for a normal install is we would be taking out the 6 screws here securing the DC bus to the IGBTs, taking out the 2 DC bus cable screws here, the support screws, and the screws on the back here where the capacitor set mounts onto the heatsink. And we would do that because we need to replace the current sensors. And I'm going to bring you down here just to show you the basics of that. Now, I won't be doing it on this particular model because I think I'm going to leave the current sensors that are in here and see if we will be able to reuse them. So the type of current sensor that we need to use is of the LEM HTFS series. And I had a real problem trying to find these because the type I was using seemed to be out of stock with most of the suppliers that I use. But fortunately I was able to find some on eBay. And of course it's the blunt knife again. There we go. So the current sensor that we want to use is this little fellow, which is a LEM HTFS 400p. And for the people that have purchased one of these from me, I have supplied a little PCB and a pigtail cable basically to allow you to take the cable safely from these little pins, because they are quite small and quite brittle. Now you can solder a wire straight to them, put a bit of goo around it and basically cable tie it to the frame of the current sensor. That will work. And what you're looking to do then is, let me grab the camera here and I'll show you. Down here you will see one current sensor. Now this is the DC bus current sensor, so it's not one of the ones that we would want to change. The two that we would want to change are buried right in there. You can just about see one of them. And these are a kind of an older type of current sensor, and they're not really compatible with the current design that we're using. So they need a plus and minus 15 volt supply, and they output, you know, a positive 5 to minus 5, which is a real pain. Now these little HTFS sensors, on the other hand, only need a plus 5 volt supply, and they output 2.5 volts at zero current and then swing above or below 2.5 volts depending on whether the current is positive or negative and the magnitude of that current. So we're basically looking to go in there and replace those black sensors with some of these nice blue ones. Alrighty, so now once you have all this stuff stripped out, you've got this little bit of metal still here, you've got your current sensors changed out, you will need to connect the current sensors. Now the current sensors connect on con 6 and con 8 on the PCB, and the pinout is basically labeled on the board. You have 5 volts ground, output and reference. You basically need to match that from your current sensor pinout to a little you can solder these guys straight in, or you can use a Molex plug to just plug in the two current sensors. It doesn't matter which sensor connects to which of the two ports, because they're not used in the motor control algorithm, rather they're used as monitoring and safety devices. So you will now have your board mounted, your current sensors connected, and the next thing that you're going to want to connect will be the heatsink temperature sensor, which I haven't brought down and I'm going to have to get for you, and I'm getting the goo on me. Okay, we'll come back to the heatsink temperature sensor in a minute. So let me just continue on. Now, the IGBT drivers connect to con 1, con 2 and con 3. And these are, I think, 8-way Molex SL connectors, which we have replicated on here. So these will pretty much just clip straight into these three connectors here, and you can't make a mistake because there's a key on them, so you can't put them in the wrong way around. So current sensors and drivers will now be connected up, and you will see up here we have a rather large terminal CON 5, and that's marked as HV battery. And what we want to do is we want to connect the DC bus from here. You can use, for example, this red and black wire here connect to the DC bus, and you can simply extend those and bring them to that large screw terminal CON 5, or you can use any of these spare spade terminals now from where we remove the these guys here. So getting there now, we'll have current sensors, voltage sensing, heatsink temperature sensing set up, IGBT drivers, and you'll basically have your board mounted in here. Now once you've got all that done, the next thing then is to connect the multi-way plug. Now on the GitHub, let me just get a bit of paper to wipe my hands, sorry. Okay, so on the GitHub you will find a file called Combi V6 pinout, and although this is the V8 board, it applies to the V6, the V7 and the V8. And so what this is it's a description of the pins on the main connector, and what they do and what we would use them for. So a couple of things that we need to have, and the last real connection that you need to make here from the internal aspect of the inverter is to this guy here, and this is going to be the motor temperature sensor and the encoder. So let me just walk you guys through this now. I'm going to just try to be somewhat organized. Okay, so I've gone back to my notes here, and basically going to tell you what colors that you connect to what pin. And again, you can just pause this, play me back, all that kind of thing. I think is just the easiest way to go. So motor temperature sensor connects to pin 21 and 22, and that is basically the white and the black wire from this pin header. It doesn't matter what the polarity is, because it's simply a NTC sensor. So you connect the black and the white to 21 and 22. Now the encoder basically has blue, green, red and orange wires here. The blue wire is the encoder ground. So if we look here, I'll make a fool out of myself, which is never difficult. You can use any of these grounds really. So for example, you could use pin 2 here to provide a ground for the blue wire. Green is the encoder plus 5 volts. So you can use pin 20 to provide 5 volts. Red is encoder channel 1, which is the one that we're going to use, and we connect that to pin 19 encoder input. We don't use the orange wire encoder channel 2 in this particular design. Now you could use either the red or the orange and connect either one to pin 19, and that basically gives you your speed of the rotor. That's, you know, what that's basically for. So once you get that set up, what you're going to want to do then is to make up your loom wire to connect this to the various parts of the car. So I'll walk through just a few of the basic things that you're going to need. Basically, you're going to need ground, and I switched 12 volts. There are some safety signals in here. For example, there's an emergency stop switch. There is, I think I only installed the emergency stop switch here. So for example, that needs to be pulled up to plus 12 volts. You have outputs then that can control things. So for example, the pre-charge relay and the main contactor output can basically control, you know, as they say here, a pre-charge relay and the main contactor. So you may need to use a relay if your contactor coil draws a lot of current. Once you have those signals in place, you then need a throttle signal, which will be connected to pin 6. We do provide a separate 5 volt supply on pin 24 and a ground on 25 that you could use to run a Hall effect throttle. Now, probably this will be stuff that we can go over again, but basically you now have your board installed and you have your various wires connected up, and you're in a position now to basically take the wires that you need to take from here and wire them into your vehicle. So that's pretty much this section completed, and we will have a look in the car now. Sorry, various things tend to go on around here. We will have a look in the car and show you kind of how I did it, and hopefully some of what I've been talking about here will make a bit more sense. Alright, so with that bit of knowledge, hopefully it'll make a bit more sense now, some of the things that I'm going to show you. So, for example, this is our encoder, connector and motor temperature sensor wired into the loom. I've used a multi-pin plug and socket here on the board, which it is pinned for. You don't have to use this, you can simply solder straight to the PCB. You will see the way we have our IGBT driver tails connected up here, as we explained. Up here we have our current sensors, basically connected to the 2 pins. With our DC bus voltage connected to the large terminal block here, and our heatsink temperature sensor, sorry that I didn't describe too well, connects to this black wire here. Things like how we communicate with the inverter via USB, and that I will describe in the next episode. But this is just basically what we're trying to achieve here, and what I've hopefully been able to describe to you. Alright, so inside our crazy test vehicle, we can hopefully kind of explain to you guys some of the basic controls that we need to wire to the inverter. So I have an emergency stop switch here, which is basically connected from plus 12 volts to the emergency stop input on the inverter multi-way plug, and when it's basically out like this, it's connecting plus 12 volts to that pin. If you don't want to use this, you can simply wire that pin so that when you turn the car on, it applies 12 volts always. You push that in, then it basically breaks the 12 volt feed. We have a 3-way switch, kind of self-explanatory, that reverse, neutral or drive, and it applies plus 12 volts either to the reverse pin or the drive pin, or indeed neither when it's in the neutral point. The inverter start button is basically a momentary action switch that basically just applies 12 volts to the system, applies 12 volts to the start pin when we give it a press, and basically assuming the pre-charge has completed properly, will engage the main contactor and basically put the inverter into run mode. And then depending on which direction that you have selected here, pushing the throttle pedal will basically cause the car to move. The throttle pedal that I've used here is a BMW E46 Hall effect pedal. It uses 5 volts DC supply and gives me a voltage output, I believe, of something like 0.7 to 4.2 volts or something like that over the entire travel range. So once you have all of these things connected up, you're basically good to go. Alrighty folks, I hope this has been good to basically show you primarily how you go about fitting the open source combi board to the Enova inverter, and also giving you a little bit of a brief history of how the whole thing came about. And yeah, so in the next episode we will be detailing how we communicate with the inverter via a web-based interface, how we set the parameters and what the various parameters do, because that'll be quite important. And that will apply to the Enova and indeed all of the projects based around that design. So, thanks a lot guys for watching. I hope you found this helpful. There will be a link in the description to the GitHub page where you will be able to find all of the files associated with this particular design, and indeed the previous versions of the open source inverter that I have been involved with. Any questions, drop a comment below, and we will see you in the next video when we will be doing the, as I say, the PC based interface and programming it. And I'll bring you for a little bit of a spin in the car too, and kind of show you some of the data logging that we can do here. So, oh, sorry, one last thing. I do have about a half a dozen of those PCBs, the bare PCBs left. So if you're interested in one of those, I'm selling them for €35, including worldwide P&P. So, yeah, had to get a little bit of a shameless commercial plug in there. So that's it guys. We'll see you in the next episode, and happy inverter building.